Have you checked?
Yes, sir.
Okay. So we'll extend. Yesterday we have seen, if you uh, consider a intrinsic material and covalent bond breaks, then one electron and one hole, that is EHP pair generated. Then what is the problem in intrinsic material? Then how to increase the conductivity in extrinsic material by adding trivalent and pentavalent atoms, we have seen. And in that we have first discussed the n-type material where pentavalent atoms are added into silicon. So phosphorus we have added. So this diagram shows that phosphorus is pentavalent atom is added at the center of this structure, where it will provide one free electron, right? One free electron, and once it is donated that electron, it becomes positive ion. So positive ion with free electron generated. So as a whole, the material is still neutral because the electron is present in the structure only. Up to this, everything is clear. Have any doubt?
No, sir.
Okay. Now we'll see a little bit about the band diagram at different temperatures. So you can see here I have shown two band diagram. Let me again draw it. Suppose I will take the band diagram of this extrinsic material at 0 Kelvin. So what I told, this is your valence band and this is your conduction band, and in between that, this is forbidden energy gap, that is Eg. Now at 0 Kelvin, semiconductor behave as insulator because all the electrons are bound electrons and not finding any free electron, and in that case the electrons are present in the valence band and conduction band is empty. Is this the case?
Yes, sir.
Yes, sir.
Now I'll make this semiconductor here. This is intrinsic. Okay, and I have added pentavalent atom, that is phosphorus. Okay, so phosphorus is added here in silicon intrinsic material. Now this phosphorus, if you see, this is plus 5 electrons are there in the outermost shell, and when we join, we have seen 4 electrons will be attached to the neighboring silicon atom. And this is the 5th electron, which is very loosely attached to the nucleus, and it requires very less energy. So let me write here 0.05 electron volt. But at 0 Kelvin, this is still attached to the nucleus. So I am finding here valence band is filled and conduction band is empty. Clear? Now, if I increase the temperature to 50 degree Kelvin, that means I am increasing the temperature, means I am giving some of the energy. So this energy actually is sufficient to break this electron from the nucleus and it will become free. Is it the process yesterday we have seen? So once this is free, this ion or this phosphorus atom become positively charged ion. Now the same thing how I'll show in the Venn diagram. Let us take This is a energy level which is just below the conduction band, and as it is require very less energy to detach this electron, let us take this is my 0.05 electron volt, and this is donor atom, so I can consider this is as donor energy level. Donor energy level. Once this electron is come out from this nuclear force, then I am getting a electron here and positive ion. Are you getting my point? This is a structural diagram. This is the energy band diagram. And whatever happens in the structure diagram, the same thing we can represent in energy band diagram. And in this process, electron and one positive ion generated. This donor level can be also represented as ED, which is shown here. You can see this is EC, that is conduction band bottom, and this is EV, valence band top, and in between that EZ, and the donor level can be represented as ED. Suppose 5 or 3 phosphorus atom I have added. Now tell me how many electrons will generate and how many positive ions will generate? 3. 3 positive ion and 3 electrons. And 3 electrons. Like this. So this process of generating electron and the donor atoms ionized are called as impurity ionization, because these donors are impurity. So this whole process by which electron and ions are generated are called impurity ionization. Or in short, I can write. So 50 Kelvin, it is detached. Now if I increase the temperature, suppose I have added only 3 phosphorus atoms, so at 50 degree it is ionized and I am getting electron and positive ion. Now still I will increase the temperature to let's say 100 Kelvin, then 300 Kelvin, like that. Then what will happen? I am still giving extra energy, so all the impurity whatever added, that will be ionized initially. Then extra energy whatever I am providing by increasing temperature, what it will do? From 50 degree Kelvin, we have seen all the 3 atoms whatever I have added that are ionized. Now I am increasing this 50 Kelvin to 300 Kelvin, means extra 250 Kelvin I am giving. So this extra energy whatever I am providing, what it will do?
The electrons in the valence band will go to conduction
Very good.
band.
That means it is breaking the covalent bond. Okay. So valence band to conduction band it is moving, means it breaks the covalent bond. Like suppose this covalent bond breaks, this will generate one free electron and it will generate one hole here. That means EHP generation started. So I'll get, let us take 3 electron here and 3 holes here, right? So this is 1, this is 2, this is 3, right? So you can observe the electrons from the bound state, now it is free. In that process electron hole pair are generated, and this process of generating electron hole by breaking the covalent bond are called band to band transition. Band to band transition. Okay, so in total, two type of process are happening inside the semiconductor when you consider extrinsic semiconductor. One is impurity ionization, where one positive ion with one electron generated. Next, band to band transition, where electron hole pair generated. This electron hole pair generated due to the breaking of covalent bond. So in this PPT, it is written the pentavalent atoms are added. That means group 5 elements are added at 0 Kelvin. You can see the donor ions are in the lower state. That means it has not generated in free carrier. Once I'll increase to 50 Kelvin, then these electrons are free, and here ions are generated. Okay, 4 ions are generated here. It has shown. As we increase, then all the atoms will be ionized. Then after that, it will extra energy if you provide, then it will break the covalent bond. Now that thing is explained here. Whatever I have shown in diagrammatic format, same thing again it is there. So this is your donor label, this is the conduction band, this is the valence band, and this process from hole and electron generated, this is uh, a circle, hollow circle, and this is a black dot. So this process is band to band transition, and this is the impurity ionization. Just now I have shown that one. And in that process, I'll generate one positive ion and one electron. So I've written here impurity ionization and band to band transition, right? Generally, this gap is 0.05 electron volt for silicon and 0.01 electron volt for germanium. Clear? Everyone has understood? I'll ask some question now. Any doubt? Then ask me. Otherwise, I'll ask some question here.
Excuse me, sir.
Yes, yes.
Sir, I have one confusion. In a covalent bond, when the bond breaks, then two free electrons are generated. Then why only one electron moves to the conduction band?
No, only one. Who told you 2 electrons are generated?
So when a bond breaks, two electrons are free now.
No, bond means you see here. This is a silicon. So 2 electrons are present to form the bond. When breaks, that means what we say, 1.12 electron volt is required to take an electron from valence band to conduction band. That means it is referred to only one electron move from valence band to conduction band. Okay. When we say covalent bond breaks, that means it is given 1.12 electron volt and it breaks the bond so that one electron will move from here to here. That means bound state to free state. Okay, it is not referring to 2 electron. That means you have to provide 2 times of this energy. Okay. In general, when we say covalent bond breaks or the EG, this is your EG, that is 1.12 electron volt. That means to take out one electron from here to here, not 2. But in general sense, you can understand one electron or reference is one electron and only one electron is removing here by breaking the covalent bond. Clear?
So thank you.
Now, we'll discuss why it is called as N-type material. I hope for everyone the concept is clear. Now, let us take here. You will tell me the answer. I have added phosphorus here. This is an intrinsic material what I have taken. How many phosphorus I have added? I have added 8 phosphorus atoms and I am providing temperature at 300 Kelvin so that what I observe 10 covalent bond breaks. 10 covalent bond breaks and 8 phosphorus I have added. Now tell me, in this structure what I have drawn, how many electrons I'll find, how many hole I'll find, how many positive ion I'll find.
10 electrons, 10 holes, 10 protons.
10 electron, 10 hole, positive ion,
10,
8 or 10?
8.
8.
10.
So electrons will be 18.
Electrons will be 18.
10 plus 8.
10 or 18? Only one has told 18, all are saying 10.
So 18 is correct. 18. 18 will be electron.
18. All are agree with that?
Yes, sir.
If anyone disagree, then you can tell. So it will be 10 or 18.
Then the hole will also be 18 if electron will be 18.
Hole will also be 18. Who told this one? Can you explain?
So because there is always an opposite motion between electron and holes. When the electron goes to the another position, the hole takes its place.
What I
That's
have
why.
explained yesterday and today, regarding that only I am asking. You contain everything into that only.
Yes.
Anyone who agree this 18 holes and 10 electrons will generate? Can you explain? Okay. Uh, who told 18 electron and 10 hole and 8 positive ion? Can you explain how you are getting that?
Yes, sir.
Hmm.
Electrons are 18 because 8 we are getting from the phosphorus ion and 10 from the covalent bond. So 10 plus 8, 18. And holes are 10 because the covalent bond is so the electron will move to the conduction band and so a hole will be created in the valence band
Very good.
and
So,
positive ions from the phosphorus.
yeah,
8.
very good. So covalent bond breaks means I told you one covalent bond breaks means one electron and one hole will generate. So 10 covalent bond breaks means number of electron will be 10, number of holes will be 10. Is it clear?
Yes, sir.
Yes, sir.
Yes, sir.
Now how many ions I have added, how many impurity I have added? 8 impurity I have added. So here in the last, here what I have told you, this impurity ionization, how many phosphorus atoms I have added, same number of electrons will generate and same number of ions will generate, because one impurity will provide one electron and itself it will become positively charged ion. So 8 phosphorus atom will generate 8 number of electron and 8 number of positive ion. So in total, how many number of electrons I'll get? Here 8, here 10. So 10 plus 8, 18. So let me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, 18 electrons. So out of that, 8 from phosphorus, 10 from covalent bond breaking. Now after that, 8 positive ions. So positive ion, positive ion, positive ion. 1, 2, 3, 4, 5, 6, 7, 8. I have drawn near to this electron because it will give an idea that one phosphorus atom gives one electron and one positive ion. That's the idea. Okay. Then 8 holes. So how I'll represent here hole as circle like this. See, you can understand here one phosphorus atom is creating this one and one covalent bond creates this one. Is it clear to all?
Yes, sir.
Now, yesterday also I told you these ions cannot move inside the material because they are actually atoms bound to the neighboring atoms with covalent bond. So these ions sorry, immobile. Okay, they cannot move inside the material. These electron and holes are mobile. Now, whenever I'll give some voltage here, let us take 5 volt I am attaching to this. Then this is positive, this is negative. Now, electron try to move this side and hole try to move this side. So I'll get a current whose direction is this, and this constitute electron current plus hole current. Yes or no?
Yes, sir.
Now number of electron is 18 and number of hole are 10. Whose current will increase because electron will give IE and hole will give IH. So definitely IE must be greater than IH or not. More number of carrier means it will move inside the semiconductor, so it will provide more current compared to hole.
Yes, sir.
So these electron I have represented here N as electron concentration, and instead of H let me write here P so that it will hole concentration. So this is electron concentration, this is hole concentration. What is concentration? I already told you. If I take 1 centimeter cube volume of semiconductor and I'll find this many number of electron and hole, that is called as concentration. Okay. So here the number of electron is greater than number of hole. That's why these are called as, electrons are called as majority carrier, and number of holes are less compared to electron. That's why they are called as minority carrier. So you can see I've written here N is majority carrier and holes are the minority carrier. I can also write here these are the minority carriers and these are majority carriers. And electron current is more than hole current if you compare in the N-type semiconductor, and that's the that is why, because N or electron concentration is more compared to hole concentration, that's why it is called as N-type semiconductor. Is it clear?
Yes, sir.
So whatever diagram I have drawn here, it is represented. This is the Venn diagram. This is the ion, II, BB, and positive ion with hole, and here electron hole I have written. So any doubt you ask me, otherwise we'll proceed for P-type semiconductor. So intrinsic semiconductor, what type of material or what type of atoms I'll add so that it will become n-type, pentavalent or trivalent?
Pentavalent.
Pentavalent. When you add pentavalent, those are called as acceptor or donor.
Donor.
What type of ion I'll generate?
Positive.
Positive.
Okay. So these ions are moving inside the material or not?
So immobile.
Immobile. Number of electrons are more or number of holes are more?
Electron.
Electrons.
Okay. This is called n-type or p-type?
N-type.
Fine. So n-type we have understood. Now we'll go to p-type semiconductor. So once you understand n-type semiconductor, the same way you can understand the p-type semiconductor. Here, atoms from the group 3 or group 3 materials are added into the silicon. Like group 3 means what? The atoms which have 3 electrons in their valence cell or outermost cell, like boron, aluminum, gallium, indium, all those are having 3 electrons in their outermost cell or valence cell. Now, let us understand how these bonds are formed. So these are the silicon, and in between this, I'll add boron. These silicon are having 4 valence electron here, and this boron having 3 electron in their outermost cell. So this 2 electron form the bond, these 2 form the bond, these 2 form the bond, and these are also extended. I'm not showing all these things. It will be extended like this. Now these 3 bonds are formed complete, but here this bond is not complete. That means to form or to create this bond, we require another electron here which is not present, or I can say a vacancy is created here. So this is your hole, and this is, all these are bound electron. Now what happens at 0 Kelvin? This is the condition. So if you look at the same thing in the energy band diagram, you see conduction band, valence band, and as it is having less number of electron, or one electron is less, so these are called as acceptor atoms. Okay, and generally it is written as +3 in the center to represent 3 valence electrons are available. So to form this bond, it is actually incomplete. So that's why you can see these are called as acceptor. It is they try to accept one electron so that the bond will form and it will have octet state. If you consider this boron, how many electrons in the outermost cell? 2, 2, 2, 6. Here 1. That means 7. It has not completed octet state. So it is ready to accept another electron to make its state as octet state. Okay. So that's why these are called as acceptor atoms. And as we denote this donor atom near to the conduction band, here we can represent these things near to the valence band, because in this process we will generate one hole. We will generate one hole. So how this hole will create? This is already at 0 Kelvin. Now if I increase this temperature to 50 Kelvin, what happens? The near bond, means near to this structure, whatever electrons bond format, will come and try to fill this gap. So in that process, what happens? One vacancy is created here. It has achieved the octet state, but one hole is created here, and this boron having 3 electrons now it has accepted extra electron. So this extra electron is not compensating with the number of protons present in the boron. So it is extra. So this boron will now become negatively charged ion. Negatively charged ion. So instead of that, you can show here negative ion and one hole is created. Suppose I'll add 4 boron atoms, then 4 ions with 4 holes will generate. These holes are shown as white dot. White dot. So this is the process. That means how many boron you will add, that many number of holes will generate, and the atoms which are added, they become negatively charged ion. Okay, so that's why these are called as acceptors, and this acceptor level is near to the valence band because hole are created in the valence band and it helps to create the hole. That's why, or I can say very less energy is required to create these holes and these ions are formed. That's why these are represented near to the valence band. Now still if I increase the temperature to 100, 200 and 300 Kelvin, then obviously how many atoms I'll add, that will be ionized and they will produce electron and hole. After that, they will start to break the covalent bond. They will start to break the covalent bond as in case of N-type material we have seen. Clear?
Yes, sir.
Structure and Venn diagram. Same thing I have written here. You can see. You see, 3 electrons are there. So due to this accepting nature, it has accepted one extra electron here, and hole is created. The hole created, acceptor atom are ionized. So what type of ions? Extra electron is accepted. That's why it is negatively charged ion, and one hole is created. How many number of trivalent you will add? That many number of electron, negative ion and hole will generate. Now tell me, if I add 15 number of boron atoms in a semiconductor, intrinsic semiconductor, how many ion and how many holes will generate? 15. 15 ion and 15 hole will generate. After that, if I try to increase the temperature, then covalent bond, as many number of covalent bond will break, that many number of electron and hole will generate. Okay, so same thing, this is also band-to-band transition and impurity ionization, you can say, like N-type material. Only thing is that this level is near to the valence band, and you see this is your band-to-band transition. That means electron hole, or by breaking the covalent bond we are getting, and here these are the impurity ionization. So hole created due to impurity ionization and hole here created due to band-to-band transition. So that name is given here, C, and here D dash. So you can understand from that. Now same type of question I'll ask again here for P-type semiconductor. Okay, let us add 9 borons at 0 Kelvin, then at 100 Kelvin, then 300 Kelvin. So at 300 Kelvin, what I observe, 15 covalent bond break. At 100 Kelvin, all these borons are ionized, and 0 Kelvin, it will act as insulator. Okay, so now tell me, at 300 Kelvin, how many number of electron and how many number of holes, and what type of negative, how many number of negative ions I'll get?
So 15 number of holes.
15 number of holes.
So 24 holes.
24 holes. Electron.
Electron will be 15.
Huh?
Electron 15.
18 or 15?
15.
Okay. Negative ion?
9.
9. All are agree with this? So this hole will be 15 or 24?
24.
24.
24.
Oh,
24. Okay. Who told 15? Have you understood why it is 24? 15 covalent bond breaks means 15 electron and 15 hole. From here, 9 hole, 9 negative ion. Okay. So in total, here 9 hole, here 15 hole. 15 plus 9, that is 24 holes. Electron 15, here 15 electron. Ion 9, here 9 ion. Okay. Clear? Any doubt?
Sir, sir,
Hmm.
sir, I have a doubt. Sir, in the previous N-type semiconductor, by increasing the temperature to 50 Kelvin, there was electron was moving out from the bond.
Hmm.
Actually, the valence bond. But
Hmm.
in the P-type semiconductor, when we are increasing the temperature to 50 Kelvin, the electron is being attracted. Why is it so? The
No,
same.
attracted means it is also moving from that bond. Na? Here you can
Yes, sir.
see when I am increasing to 50 Kelvin, this electron is attached to this nucleus or bonding structure. Okay. Now here it has a vacancy seen, so it try to fill this vacancy. In that way, it will fill here and hole is created. You can this is logical concept. You can also understand that this hole actually, if you don't understand like that, you can directly say the hole is created here. Okay, hole is created here, but how you will justify that ion is generating? So that's why actually inside that this happens whenever you add here, then to fill up this gap, some electron will move. Like in a classroom, if you are sitting and from the front bench suppose someone has left, then obvious thing is that the next person or who is sitting backside of that try to fill that gap. So it has to fill this gap so that it will have octet state, but in that process hole is generated here. So you can say hole is created and this atom becomes negatively charged ion. That process is happening here. How many number of boron will add, that many number of holes will generate, but directly the holes will not generate. This is the way how actually they'll fill this gap. In general, you can say how many holes are generated, vacancies there, that's why it is hole. But in practice, this is the way how it is generated and ions are formed. Understood?
Yes, sir.
Because it requires, you can see this acceptor level also, it requires some energy to generate the hole. It's not like that you just add these borons and it will generate, otherwise the acceptor level will be here. It is here means it still requires some energy, so that energy is provided when we give 50 degree, so that this any of the neighboring electron will replace this one and it will generate hole. So I think P-type and N-type semiconductor concept is clear to all, because this is very very important. When you go to PN junction diode, this P-type and N-type material actually join together. This is P-type, this is N-type. So here, what the carriers are there, what are the majority carrier, what is minority carrier, and how ions are, what type of ions are there, you need to understand. Then only you can understand this PN concept. Now tell me, in P-type, what are the majority carrier?
holes.
Holes,
Minority,
Electron.
electrons,
ion,
negative,
Negatives.
negative ion. N type,
Positive ions.
positive ion. Majority,
Yeah.
Electrons.
electrons.
they are holes. Okay. Now we'll discuss little bit mobility and conductivity. So conductivity means the way the carriers are moving inside the material, and by application of electric field will move. One diagram is shown here where these are the free electrons and these are the ions. Now if I connect the voltage here, positive, negative, so electrons will move in this direction and ions are immobile. So the net moment of electrons will be here and current direction will be this direction. Okay, so it is written here in crystal lattice large number of free electrons are available which are moved in random fashion. Random fashion means if I take any of the semiconductor or conductor or anything, lot of electrons are available. Okay, even if conductor if you take or semiconductor room temperature, it is sufficient to break the covalent bond and electrons will find. So these electrons at thermal temperature means 300 Kelvin or room temperature, there these electrons have some energy, self energy, and they move randomly inside the material. That means this electron may move this side, this will move this side, this will move this side, this will move this side. There is no directed movement. So net movement of these electrons are ultimately zero. That means we cannot say the net moment of electrons from this side to this side or this side to this side. No, because one is moving this side means maybe other one will move this side or this side or this side. So if I consider whole or net moment of all these electrons, the net moment is zero. Okay, that's what is written here. A lot of free electrons move random fashion at room temperature and net moment is zero. Right? Under the influence of electric field, that means if we connect the voltage here, then only the electrons will move from one side to other side. That means it is positive, it is negative, means obviously this negative potential will force these electrons from this side to this side, or this positive potential will attract these electrons, and overall the net moment of these electrons from left side to right side. Okay, and in that process collision will happen because ions are immobile, and in this collision the energy will lose, and the energy which is released by these electrons are in the form of heat. So that's why the device actually what we are using, that will heated up. Okay, because the carriers are moving inside the material and it will collide means energy transfer will happen, and that energy transfer in the form of heat. So if you use any device like mobile also you are using, laptop you are using, so some power dissipation will happen and it will get heated after some time. But how the electrons are moving inside the material, if I want to describe, then we'll go for mobility. So mobility means the ability of electron to move inside the material, or how much mobile is the electron, the way it will move inside the material, that decide the current inside the semiconductor. In general, if you go to definition, I think you know this formula, V equals to mu E, where V is the drift velocity. This is called as drift velocity. This is mobility. This is electric field. E is electric field, you know. So what is drift velocity? We'll come to that, but very briefly I'll explain here. When we go for drift current, I'll explain this one. Suppose the electron, this electron is present and it is the motion is random. That means let us assume this electron is moving in this direction. Okay. Now if I connect here plus and minus voltage by some voltage or battery, then this negative potential will try to force this electron towards right side, left side, and this positive potential will attract this hole in the right side. So this movement, whatever I have shown, instead of moving this way, it will tilted to, it will force to move in the left hand side or left side due to this effect, due to the effect of electric field. Are you getting my point?
Yes, sir.
So this is called as drift moment of carrier. That means it is drifting or by force it is drifting from right side to left side. So the velocity at which it is drifting, that is called a drift velocity, and this formula v equals to mu e is satisfying. Now from here if you want to find mu, then it will be v by e. So if I write or form this definition, the mobility of the carrier is defined as the average drift velocity per unit electric field is mobility. V by E, that means if I take 1 unit of electric field and I will count what is the average drift velocity of the carrier, then I can found this mobility. So V equals to mu E, and you can generate this one. And this velocity you can see proportional to electric field. In other sense also you can find like V, how much velocity the carriers will move, the amount of voltage will give. So V proportional to E. Okay, V is proportional to E means if I apply more voltage 10 volt, then definitely the carrier will move faster or velocity will be increased. So V proportional to E. If you remove this proportionality constant, then we have to make a constant here, which is actually mu E. So this is constant for a particular temperature. If temperature increases or differ, then it will differ, but at constant temperature mu is constant. Okay, so this proportionality constant we can find, and we can form the definition as average drift velocity per unit electric field. Is it clear?
Yes.
Now, for hole and electron, little bit difference. The negative sign is here. For hole, you can see here Vd or drift velocity for hole is written as mu p into E. So mu p means it defines mobility of hole, and mu p is equals to Vd by E. That means this is the average velocity of hole divided by electric field, that is mobility. For electron, negative sign is given because the electric field direction and movement of electron in opposite direction. So that's why this negative sign is placed here. But hole, the same direction, the electric field direction, the holes will move. That's why positive sign is there. And the unit, if you want to find, the velocity unit is meter per second, electric field volt per meter. Then if you divide, then you can get meter square for volt into second, I think. Okay, so this is your unit. Here division is given. You correct it. Here it is written meter square or centimeter square per volt into second. In general, the mu n for electron is 1350, and hole it is 500 centimeter square per volt into second. Okay, means that is for silicon. But if you consider any other in the exam, you'll find different materials, and that data will be given in the question. But at room temperature for silicon, it is 1350 or 500 per hole. And it is written one point that as temperature increases, the mobility decreases. Okay, that means if you increase the temperature, more and more collision will happen inside the semiconductor, like ions are present, electron collision, electron hole collision, atom are present, neutral atoms are there, so they will collide with this one. So all these effects will decrease the mobility. So at higher temperature, the mobility will decrease, or the conductivity property of the semiconductor also decrease. Okay, that means extreme high temperature, but normal temperature it is okay. So okay, so any doubt from today's class? We have discussed p-type semiconductor, n-type semiconductor, mobility. Any doubt from this? You may get short question from here. They will give what is the drift velocity, what is the electric field. They will find what is the mobility of the carrier, or mobility will be given, electric field will be given. Then they will ask the what is the drift velocity, or vice versa. Means the electric field they try to find.
So could you please explain this point once again? So as
Which one?
temperature one.
Temperature one. So generally, suppose I'll take a semiconductor here. Let us say electrons present, holes are present, positive ion or negative ions are present. Okay, if I add pentavalent and trivalent both in a semiconductor, then obviously I'll get negative ion as well as positive ion. In addition to that, the crystal structure is there. That means neutral atoms are also there. When I increase the temperature, that means I'm giving some force to this or energy to these electrons. So these electrons will move inside the semiconductor. Okay, let us take. I'm giving here negative, here positive. Some voltage I have connected, and the temperature is increasing. So these electrons will move. So when it will combine with this hole, then they will get neutralized. Maybe this electron will strike to this electron. So when electron and electron will collide, what happens? The speed will decrease, and they will release some energy. So in that process, heat will generate, and the speed will decrease here, or velocity will decrease. When electron will collide with this neutral atom, that will also hamper the velocity. When this electron will collide with this ion, that will also decrease its velocity. So in that process, if velocity decreases, then the mobility also decreases. Due to this, all these type of collision, electron collision, electron ion collision, electron atom collision, or lattice structure collision. So all these things decrease the velocity or mobility of the carrier. Understood?
Okay, sir.
When you run towards anyone and collide, then obviously you will pause sometime, then again you will start to run. Okay, so in that process, what happens? The velocity will decrease. The same concept is here. So I hope everything is clear for all.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
So
Yes, sir.
we'll continue from this in the next class.
So what about the attendance?
I'll take, just wait. Okay, attendance was taken. Actually, in the SAP portal, attendance is not showing. Once it will uploaded, then I'll update the attendance. So till that time, you just wait. I have already taken the attendance. You can leave the meeting. Thank you.
Thank you so much, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.